All right, it's online. All right. Hi, everybody. Hello, hello. OK, so we'll talk about tuning queries in Nickel this afternoon. I'll introduce myself quickly, and then we'll dive right in. I've got lots of demos, so please do cross the legs, fingers, whatever gets us the right level of connectivity so nothing drops. I had issues. I think there's some Wi-Fi connectivity issue up here on this floor, but hopefully things will work. If they don't, this is going to be a very short talk. So my name is Cihan Biyikoglu. I'm a product manager at Couchbase. I work on the server product. I'm a bit of a database geek. Has anybody been to one of my talks yesterday? Oh, quite a few. OK, all right. Repeat customers. I love it. So I won't spend the time asking the Informix and Lustra SQL Server question anymore. But we'll dive right in. This one, I love this topic especially. I spent a lot of time doing benchmarking at SQL, TPC back in the day. Performance tuning is one of those things that you can do forever. It's like you never have to stop. You can always be better. So it's one of those very fun topics to talk about. I'll try. Obviously, we don't have endless time. I asked for like 3 hours when I actually set this session up. They wouldn't let me. So we're going to try to do this in 30 minutes. Let's see if we can do it. There's a couple of goals here. I just want to show you architecturally a couple of the options that you have for setting up things when it comes to query execution. This topology setup of your cluster actually impacts the throughput and the performance of your queries quite a bit. So we'll start there. We'll look at the execution plan, just like the classic kind of, if you're a classic database guy. Has anybody worked with Oracle before? OK, SQL Server, quite a few. So you guys know the execution plans. You guys know what the execution flow looks like. But I just want to show you our version. And pretty much the sentence is going to end with, well, it's the stuff you know. It actually looks very similar to what you actually know from those databases. But there's some interesting tricks to understand in our case. It's a distributed system, not a single monolithic system. So I'll talk about a few techniques that are really important to remember, and that's what we'll close with. So architecture first, and then we'll dive right into the queries in the second part and a lot of the demos as we look through kind of execution plans and a variety of tips. I have to mention that this is a product or is in development, so there could be changes that we make from this point on to the final finish line. So just be aware that there may be a few things that actually change by the time we're done with the product. I'm sure you've seen this before. It is the architecture at a kind of 10,000 feet level view. We have the cluster manager, which Dave talked about just a second ago. That sits at the top of the cluster, governs everything, and then a set of services on each node. And it gives you this kind of fine, nice picture, colors. You can obviously control the amount of hardware you get for each one of these nodes or the number of nodes that you want to get for this cluster. And the clients kind of are smart enough to know where the services are. They'll actually kind of communicate and know what to do without you having to tell them about this topology. You can continue to change it. Now, one of the interesting things that is, I know I keep coming back to this point, is obviously having these services. We give you the option to turn them off on specific nodes and create these zones where only the data operations or only the index operations or only the query operations execute. And by doing that, you get the option also to choose specific hardware for that given zone. So I could actually take the two middle nodes. I could say indexing service. Well, it turns out I actually like to give it a little better I/O throughput. So I'm going to put some Intel and NVMe drives underneath it, and I'm going to run it at blazing speeds. And you could do that. You could pick different amount of memory. You could pick different amount of CPU or core capacity for each one of these zones. But our still guiding assumption is that you're going to not break that within the machines within a given zone. So We still expect some of it to be unified, but you now get a lot more options as to what type of hardware you pick. So with that picture in mind, let's kind of start looking at query execution path and what that entails to understand how kind of some of the scalability, interesting kind of scalability knobs are. So number one, the connectivity to the query service happens through the REST API. It's stateless. The number of nodes that are running that service could be all the nodes or it could be some of the nodes, but we're going to round robin and load balance across them. We're just going to randomly pick a node and go to it. And essentially, query service will respond, so your connection will last until the end of that execution. And then you're going to come back with another request, and we can do that. One of the important things to remember is we're actually going to add the capability to prepare statements, just like you had this. So if you look at the execution plan, the first phase of it is actually parsing the statement. We need to parse the statement to understand what you're actually talking about. Once we parse it, we come up with an execution plan. Now, execution plan, the smarter the optimizer get, the more time we actually spend evaluating a variety of different execution plans. And for that, it could actually grow in time. The smarter you get, the longer it may take for you to be thinking about what you're going to do and how you're going to execute the plan. So there's a fine balance of how smart you want to be. But you can short-circuit this through a prepare statement that actually will prepare the statement, create an execution plan, and that execution plan is what we execute every time, so we don't have to think. It's muscle memory. We just pull up the execution plan and just execute it, and that's an important way that you can actually make the queries run faster. That's one phase you can eliminate. The second one is consistency dials. The important thing about connectivity is when you connect with a query request, you actually express what consistency level you expect. Now, in our case, indexes are eventually consistent. We don't, unlike a relational database or some of the other NoSQL databases, we won't wait until your index catches up with the insert at the time of the insert. So you can actually say, I'm going to insert this 5 rows. We'll say, all right, thank you very much. We'll update the indexes when we update the indexes. Now, at query time, however, you get the option to say, I'd like to wait until a given time. And typically, to this day, it's been, if you've used views, it's been about mentioning it at the time of the request. And you could actually say something like, I don't care about consistency, so give me what you have. Or you could say something like, I'd like the index to be consistent up to the moment of my request. So if it was 10:01 on a Monday morning, I actually like to wait for the index to catch up to everything that happened up to that moment. And then I want my query to start. But we give you a lot more dials with the next version of the product with nickel and GSI indexes. And those two actually allow you to specify times that are much wider in spectrum. You can actually pick any time if you actually know about a moment in time where you actually made an insert, you could actually specify that. And we'll take a look at that in a little bit. But these are the important things to remember at the top level to really understand how kind of the execution at the top level when your request and response comes back. This is the execution flow. The only thing I'll mention, I'm sure you've seen this execution flow a few times. This is where we actually take the plan and parse it, and there's an execution plan that you generate. And there's a whole bunch of operators that will take your query and operate on it. It's like filters and joins and everything else. But the boxes that you see that are fragmented on these kind of columns represent the parallelization that we do for some of the operations. And that actually depends on whether there are 4 or 8 or 16 of them, depends on how many cores you have on the machine that's running the query service. Excuse me. And the intra-query parallelism, thus, is very much impacted by the type of node you pick for running the query service. So it's important to remember. It's also important. We'll actually take a look at these operators, but we'll actually take a look at some of the operators that are very important to understand, and we'll talk about them when we get there. But just remember that the type of node that you pick dictates the intra-query parallelism that you will actually get out of us. So scaling query service, you can certainly start with this topology. This topology represents the index service at the top, the query service in the middle, and the data service at the bottom. All services run on every node. This is kind of the homogeneous scale-out case, right? Every node takes a slice of the workload and runs. Now, the good thing is you're going to have a lot of query nodes. You get 50 if you actually have 50 nodes, right? But the thing that is interesting is that not every query's expense is the same. And the competition that exists is if you're getting a lot of insert, update, and deletes, and if you're getting a lot of queries at the same time, or if you've got waviness about how many of these things you get at any moment in time, there is competition between these services. And that competition means that these workloads are going to collide, and they're going to go after the same resources. It's the same set of CPUs, it's the same set of memory, it's the same set of I/O subsystems that they're going to go after. You could also do this. So the previous is perfectly possible. You can do that. But we think in terms of being able to isolate and kind of control things, this topology actually will work better if you're sensitive to latencies. In this topology, you get two things. One of them is you dedicate specific machines that are going to run the query service. The other option you get is to pick a different type of hardware that you will actually use for this specific service. So for the query service, it turns out if you add more CPUs, that actually increases. Let's say the rest of the nodes could be running on 16 procs, and you get 32 cores for this. You're going to get a parallelism of 32 cores up to that level when you're executing complex queries. And that's actually important when you're fetching data, when you're doing complex aggregations, right? Those are kind of important things. Well, you could actually add some RAM, and that green section at the top could actually represent additional RAM that you can add to this box. Guess what? If you're actually going to have a lot of large result sets that you're going to return back out of these services, it's actually good for us to have that RAM because we can actually have much larger intermediate result sets that we maintain as we kind of go through the processing of each operator in the execution plan. These intermediate result sets are maintained in memory, and the more memory we have, the better we'll actually do in that case. You can add more nodes. That gives you a lot more parallelism. You can load balance across them. So it doesn't mean that because you're scaling the RAM quota or RAM capability on a given machine that you can't continue to scale up. You can continue to scale up, and you can get that. And it's actually better for availability if you give us more nodes. The impact of one node failing out of 4 versus one node failing out of 8 is much less in the dropped capacity. It's 25% versus 12%, right? So from an availability standpoint, we still want you to do scale out. So there's a whole bunch of advantages to actually doing certain things in this topology to understand. Now that was the query service, and I want to quickly talk about the index architecture as well before I kind of dive into some of the examples. There are 3 types of indexers we have in the next version of the product, in 4.0. The first one is the new one, that is the global secondary index that runs inside the indexing service. The other 2, the data service is where they actually run. The spatial one is not so interesting from a confusion of choice standpoint, because if you have a spatial query, that is the index that will actually give you that capability. But when it comes to views and GSI, there's a whole bunch of interesting choices that you can make. Which one do you choose? Is it GSI, or depending on the query, there may actually be interesting things? I talked about this yesterday, so I'm going to briefly highlight the 2 important things, and I think this question comes up quite a bit. I want to kind of put this up just for a second so you guys know. But there are reasons to use views, and there are reasons to use GSI, the new indexing. And some of them depend on the workload that you want to execute. It turns out that if you're doing complex reporting, or if you need, some people actually use views as almost a pre-computation engine or a trigger that will actually pre-calculate some answer. And in those cases, views actually work really well. They have a reducer. They can be JavaScript. There's a lot of logic you can bury in that. It's expensive for us to calculate, but we will calculate it as we build the index. And that means when you ask the question, it is ready to be answered. It's not just calculated just in time. Versus when it comes to workloads where you actually care about the index lookup scan throughput or index scan latency, or if you're looking for a secondary lookup case where you're really just looking for another attribute, let's say email, that you want to look up by instead of the customer ID that you use for your keys, these cases, GSI actually works extremely well. It's actually built to be exactly this type of an index. And the tunable consistency argument, we talked about that. The mentioned flexibility does not exist on views. Views will actually default to stale equals false. But GSI can actually do a lot more in terms of consistency settings, and we'll actually come up with an example. So the reason why these two differentiations exist is because there are architectural differences between them, and capabilities are different. So storage and caching are definitely different between views and indexes. There's ForestDB under GSI. There is CouchStore under views. That will change over time, but for 4.0, this is the picture. Partitioning model is different. Align it to the distribution of the data, not align it to the distribution of data, and independently scale it. So GSIs give you that independence. The scalability model, again, because of the index service and the ability to kind of scale these things independently, you can actually build a different type of node for the indexing service and GSI, but you can't do that. When you actually up the nodes in capacity, you're actually giving capacity to both the data service and the views at the same time. There are ways you can control certain things, but again, we're running on the same machine for the most part. And scatter-gather, the cost of scatter-gather is well known and understood. Sometimes you'll actually go from 10 nodes to 50 nodes, and you'll see your queries slow down because network is actually slow. Local processing is a lot lower latency when you can actually process more locally. Versus the network is unpredictable. And in many ways, it actually is much slower than the local processing. So it is for GSI, you get the advantage of not limiting the kind of fan out, the wider fan out that you have to do. And it essentially allows you to limit the fan out, even if your data service, which benefits from 50 nodes a lot, right? Even if your data service happens to be a fairly wide one. So these are some of the differences, but we'll actually talk about this topic quite a bit in the upcoming white papers and blog posts, et cetera. So follow up if you want much deeper kind of understanding of what these are. When it comes to index service scalability, there's a couple of things to remember. So I'll start with the same picture. You can do this. You can have the index service and query service and data service all running on all the nodes. That's perfectly possible. We expect people will start this way a lot. It's good to load balance across all of these nodes. You can actually dictate where the indexes are created. You can spread them over to these nodes. The problem, again, is competing services. The more you insert, the more the data service has to do. But at the same time, the index service has to maintain. I mean, they're pretty much kind of competing for the same resources on the same machines. So they're going to have to do compete for the same resources. It's the same set of CPUs. It's the same set of memory that they're after. Versus you can also do this, which is the isolated topology, where you can actually take out the indexing service to a separate subset of nodes. You can control the hardware you allocate to it. And why would you do that? Well, it turns out there's a couple of reasons. One of them is you can actually add more RAM and give indexing service a little more RAM. That actually will help cache the indexes in memory. So a lot of, again, as I said, we're kind of very memory-centric in our architecture. A lot of the defaults are based on being able to insert into memory, and you don't have to wait for persistence to disk, or you don't have to wait for replication. You can if you want, but you don't have to. And indexes are eventually consistent, and at query time, you can actually ask for consistencies. But if you were to cache a lot more of your index, you could actually respond to things much faster. You respond to query requests much faster. If you add more CPUs, we're actually going to be able to do a lot more scans in parallel. We're going to give you the ability to also maintain these large number of indexes on a given node if you can actually give us more CPUs. Now, giving us a faster I/O path on the indexing side, it will actually help. This ForestDB loves SSD. It actually works well on Rust drives too. But SSDs specifically will actually give us a lot of performance boost. So you can actually choose a completely different I/O subsystem if you wanted for the index service nodes. You can also continue to add nodes, and that scale-out capability is always there. You can actually choose to scale out for availability, obviously, and for load balancing. That's important to maintain. So that was part one. I just want to kind of dive into part two, which is more about the optimization and the execution of queries. So we talked about mainly scale to this point. Let's kind of focus on the execution plan. So this is the queries execution plan. Hopefully, this is something you guys already recognize from a previous database. But we actually can give you this output through an explain statement. We'll actually see how to do that. But we essentially have a bunch of operators that takes your select star from blah statement and turn it into a sequence of operators. You see some blues and greens up here. Blue boxes essentially represent the things that are kind of assembly operators. They really assemble the operators together and how we actually want to execute them. So sequence means I'm going to actually sequence a whole bunch of operators and operations together. Parallel means I'm actually going to take the set of operators and I'm going to have a bunch of threads that are going to fire up, that are going to do part of the work, and then eventually, at the end, I may actually reduce it down to a single-threaded operation to finalize it at the end. The execution flow, even though it actually looks like kind of there's a box and an arrow that's stabbing the next box, it actually is a very streaming-oriented operation. There's no stop and go here. You essentially have an operator like primary scan starting to scan and produce immediate results, passing it on to the next set of operators. So as I take things out of the primary scan, I can actually pass it on to the fetch, which is the next kind of set of rows on the green up here, right? And essentially, some of these things can be live, depending on how long the execution is, all at once. So imagine this not as a sequence of things that are happening one at a time, but they're actually streaming to each other a set of results, and the query output can actually come out fairly quickly. Let's take a look at a couple of the important operators. These are not going to be excuse me, super surprising either, hopefully. Scans. These are fundamental ways in which we actually kind of do the operations when it comes to kind of reading. And the primary scan essentially means we're going to the primary index. The primary index, again, is the index that has all the document keys in a bucket. There's no where clause or a filtration that you can do. It's, if you have got a billion documents, it's got billion keys in it. So it's not as effective to scan as a secondary index, which may actually be purpose-built and may allow you to filter certain things along the way. So primary index scans typically are not great things most of the time. So if you see them, there's a chance for optimizing right there. Index scans, on the other hand, point to things where there's a secondary index involved. And if you actually end up scanning that, well, it actually is much better because that is an index that allows you to target much smaller amount of data, much smaller amount of indexes, especially if there's a where clause in there. Fetch operation is essentially the operation that we do to the data service from the query, where we actually say, we've got the document key. Let me go get the actual document. The index may not contain all the attributes inside the document. We may actually do the fetch to bring in all these other attributes that are hanging off of the version of the truth, which resides inside the data service. The version of the truth resides always in the data service. The indexes can be out of date a little bit in terms of information. The projections, fairly easy to understand. At the select statement at the top, you actually project a number of different attributes. And you do not always say star. So the projections essentially happen along the way. Sometimes we need certain columns because they are in the where clause or in the order by, but they're not in the final output. So we'll do an initial projection to reduce the result set that we're tackling, the intermediate result set we have to maintain. At the very end, we may actually do another projection, the final projection, to boil it down to only the things that you actually ask for in the select kind of projection list. Yes? It does contain the projection. So does the query plan include projection operation? It does include the full kind of length of all the operators that we do. So yes, the projection statement is actually there. And I'll show you in just 1 second that it actually shows up quite a bit. You'll see it quite a bit happen. These are there's quite a large list of operators. So I'm not going to cover all of them, but projections show up so much that you'll pretty much see it in every execution. So there's an assembly set of operators. These are kind of sequence and parallel. As I said, they actually assemble the rest of the operators and how we execute the execution plan. So it's good to understand what they do. But for the most part, what you want to do is look at what they're containing. And if you see a sequence, then you actually see kind of the assembly together. If you see parallel, just assume everything that's encapsulated under parallel to be, the output is JSON, so you'll be able to see the containment. But that containment essentially represents things we will do in parallel. And filter, these are kind of operations that allow you to reduce the result set. Very important in terms of performance. And it's great to have these pushed down early in the execution plan. So the earlier some of these things happen, the better it is for you. Filter is obvious. It's the where clause, wherever you specified what you want to filter on, that's what we filter on. Limit is about limiting the number of records that will actually output, the number of items we'll actually push out. Limit may actually show up at the very end of your execution plan, but it will communicate back up the stream that it actually only needs about 10 items back, right? And it will inform the operators up the stream that it has enough data and they can stop. And at that moment, the execution actually halts. And once we have enough data to return to the client, they only ask for 10 rows. We can actually stop and return that. Offset is just limit for paging, but you can essentially start in an ordered set, you can start at an offset of 20 and then only return 10 rows. So 20 to 30 is what you return. So offset allows us to kind of skip a set of things in the beginning. Join operators are interesting. Join obviously allows you to combine two documents into one, much like relational databases. Now, it's interesting to see that in a document database, but you actually have a lot of cases where orders and products and customers are not really entities that you want to put into a single document. That level of denormalization is unhealthy because you will explode the size of your data. So for a lot of people, it's actually important to be able to join and reshape the output and be able to return that. So products and customers, it's good to actually be able to join those things many days because you want one or two attributes out of the customer and you want a couple of attributes out of the product. It's actually a good thing to do. Yes, John?
Yeah. So when you design a sort of set of buckets, multiple buckets, can you have within the same bucket multiple keys, multiple types of keys, and then be able to join them? And then how?
Yeah. So for the broadcast, I'll repeat the question. The question is, if you have keys that are mixed types within a single bucket, can you actually join across them? The answer is yes. You can actually do this across buckets, or you can do this within a bucket, and you're allowed to reference anything in that. Within a single bucket, it will actually, I'll show you the example. It looks like a self-join. So you can do self-joins in relational databases, and in our case, bucket contains a lot of things. But in one instance of the bucket, we'll actually look at types of beer, and the other reference of that bucket is going to return to things that are breweries. So breweries and beers can actually be joined, and I'll show you that exact command. So yes, that's very much possible. So nest and unnest are interesting because we have complex data types. Unnest essentially takes an array and make that kind of a regular output, part of the item output, and unnest will actually do the reverse. So it essentially allows you to manipulate and pivot a collection of items into either an array output within a single item, or you can actually turn them into many items and output them as that. So let's start getting into the demo. This is the first one, and what I'd like to show you is a very basic statement. I think I may have to miss that. Let's see. I think I have the statement right up here. So this is I don't know if you guys can read this, but I'll read it out loud. Select name and updated from beer sample, where type equals beer. And I'm going to order by and limit this statement. So when I run it with explain, the query is not executing. It's just outputting what the execution plan would look like. And we talked about some of these operators. So you see the sequence operator at the top. Well, it's there. There's another sequence that actually will package another containment boundary. There must be another parallel that is actually going to happen later. So this one happens to do a primary scan. It's an index called P1. That's the primary index that I created on beer sample. And it is of type GSI. The key space, which is the bucket, happens to be the beer sample bucket. And the next operator happens to be parallel. It's actually going to sequence a set of things, operators. Again, there's an enclosure that kind of says these operations, the fetch, the filter, the initial projection are going to be things that we will actually parallelize together. They essentially get represented as a separate set of operators, but it's fairly obvious from reading the rest of this what we're actually doing. We're filtering on beer, a type equals beer. Well, that's actually good. I'm actually going to project things, and only name and updated were the two that I really wanted to send out. So that's pretty much the first demo. This is the explain. It's fairly easy, hopefully easy to understand. Now, let's take a look at a couple of techniques, and I'll walk you through a couple more as I talk through it. So first one is, it's obvious, but I just want to repeat it. It's minimizing the items that you scan. Now, it is interesting. One of the things that you'll actually see if I go to Couchbase, this is 4.0. Under buckets, I can actually look at some of the statistics for beer sample. Let me kind of minimize this. If I actually take this statement and run it without the explain, you'll actually see that when I run this statement, I can actually go and see the data service kind of returning a set of data. It turns out about the peak hits about 6,000 over here. So what happened is the index, there was a primary scan. We actually got all the keys. But then the operator actually was fast enough to go grab and fetch a lot of these records out of the data service. And the data service just reported the fact that we just scanned this many items. And there were gets, this many gets essentially that came into the system. So it is fairly, you can actually see a lot of what's going on inside the area. The interesting thing is if you create an index, you can also see it drop. And if the demo gods are with us, we'll actually see it happen. So what I'm going to do is, we just ran this statement, but I'm going to create an index on type. We'll call this I_type, and this index is going to give us a bit better performance, hopefully. So that was about 6,000. Let's see if I can take this create index statement here. This is the one that creates it. Takes about 10 seconds, but let me copy my next statement so you don't have to painfully watch me type. Though that would have been fun too. So what's happening now is it's creating the indexes. It just took about 11 seconds on a small amount of data. This can be done, by the way. It actually blocks here, but you can do this asynchronously. You can just kick it off and leave if you don't want to wait for it to come back. But this next statement is exactly what we were running. Well, I shouldn't say that. There's actually a slight bit of a change. There's a filter here that I'm doing. So why don't I do this? Why don't I change that a little bit? So we run the identical statement here instead. I'll cancel out of this and just do this statement. Oops. Let's try that again. All right. So let's go back to the environment. It actually is hitting up a little bit less. So there's a number of, I don't know if this is actually the difference that I'd normally see, but essentially the peak that you're seeing has now dropped a little bit in terms of what the index provided. There's a lot of beers in the database, but there's quite a number of breweries as well. So now we don't, because there's an index scan involved, we don't have to go and scan and deal with the document keys that actually represent breweries anymore, because the index actually helps us. One of the other things that's interesting to look at is the explain statement. So let's take a look at this to see if it actually used the index. Now, instead of the primary scan, if you kind of scroll up to the top, instead of the primary scan, what you're now seeing is that this new index is in use. So iType index is there. We're actually scanning that. That's great. It actually is represented as beer high and low. So it's just a representation of a range, but we just happen to kind of use that analogy to kind of generalize the scan operation. The rest of it looks pretty much the same, but because we're using that index, we actually see a little better benefit in terms of the execution of it. Now, one other thing I want to mention before I leave this topic is the fact that you can actually hint indexes to us. there's going to be multiple indexes that are involved. There's going to be multiple where clause predicates that you will specify, like the one that was here. And in these cases, there may be multiple options for us to choose from. Now, if we're not picking the right index, you can actually tell us to pick the right index, and that is done through the useIndex hint right here. UseIndex hint has to still specify the name of the index and the type of the index that needs to be there. So just remember that you can actually do hints within the environment. One other important thing I want to mention before I leave the kind of indexing topic is the fact that you can have multiple indexes. I could, for this query, when I actually query across these two different types of predicates, where type equals beer and ABV is greater than 0, what I actually can do is have two separate indexes. I can have a beer index and I can have an ABV index. That's one option. What we'll do is we'll actually use both of those indexes, and if it turns out that one of them actually scans much faster, we'll stop the other one and use the keys out of that to essentially combine and fetch the rest of the result set once we actually have that. Another option is that you can create a compound key. You can actually say an index that has type and ABV inside it, and that compound index can actually return the results. And depending on the selectivity and depending on some of the distribution of your data, it actually is beneficial to have either a compound index or two separate indexes. Two separate indexes can actually give you a great deal of flexibility as well, because the secondary column on a compound index is not something you can easily filter on, but a separate ABV index would actually give you. So you're now seeing the world of the type of indexes to choose and the amount of options you actually get. These are not all that different from a relational database query tuning exercise, but you have to consider all of these options, and all of these capabilities are there for you to kind of evaluate. So do take a look at these other options and understand how they impact your performance. The other thing is you don't create an index per query. You obviously want to create the indexes that will benefit the most amount of queries in your environment. And for those cases, there may be other types of compromises that you want to actually play. So just remember all of those things about query tuning. And this is why I asked for 3 hours to present this thing, but we gotta move on. So we talked about index hints, and it's important to remember that they're there. There will be cases, I'm sure, that you'll actually want to force us to do the right thing. Now, when it comes to minimizing the amount of items we actually work with and the intermediate result sets you have to tackle, limit and filter come in handy. So it's a good practice to actually kind of push limit into everything that you do, but it especially helps in the cases of joins sometimes. And this example I'll show you actually has these two queries. Now, let me just pause and explain this query for a second. The query actually is joining exactly the question that you asked, John, which is kind of breweries and beers. It happens that both of them are in the beer sample database. So I'm actually referencing it twice as B1 and B2 in this case. I'm returning a whole bunch of different interesting information about beer and brewery from both of these types of documents. And I'm limiting on B1.ABV greater than 0. This is kind of a, if you're a beer fan, it's a measurement of some sort on the beer, of the quality of the beer. I won't make up what that is. I'm not an enthusiast. But it essentially will give us a query that joins these two different types of data. All right, so the result that comes back, fairly efficient. It actually returns the beer name, the brewery name, and the country that the beer is from. I got to give it up for Belgium at the top, because that's my favorite country for beers. Anybody from Belgium? Excellent. Thank you for the beer. So this was one example, but what I'd like to add to this is a specific addition where I'll actually say, look, this first table that we're joining is going to be just containing the type beer in terms of documents. And what I'm going to do is take the beer documents, and I'm going to use the beer documents key, the brewery ID, and I'm going to use that to join it back into the brewery. So if you read this syntax here, at this line, the join statement, what it actually does is it defines essentially the B1 key of brewery ID and takes that and makes that the join key for B2. So what we're doing is we're picking up brewery ID out of the beer document and then going back to the document keys and saying which documents have this key. And it happens to be attributed as brewery ID in the documents. The only addition I'm making is this type equals beer. And with that, what's going to happen is we're going to see that the time actually drop. Because what we've just done is tell the environment that for the indexes and the keys that those brewery IDs, it doesn't have to go look at the primary index anymore. It can actually go look at the relevant index that contains the right keys and just returns those into the join. And the join will actually go back to the document keys and grab them out of the data service right there. So that's important to remember. And filters, so just adding this explicit filter, even though it actually would have worked fine, even if we actually didn't add the filter, because brewery ID doesn't exist anywhere else but in the type beer, it was actually beneficial to add that filter explicitly into the mix. So be explicit about your filters. Continue as you mix types inside a bucket. It's very important to actually continuously filter. Now, one word about joins. They're actually efficient by nature because of just the explanation I gave about how we do joins. Joins cannot be done on two random keys that exist inside two different values. They actually are done through a nested loop kind of operation, if you're familiar with what that is, between the attribute of one input, the left side of the table, nested loop, and the document key is used for joining in. That means we can actually go and very directly find these document keys because we have a primary index. We also have the data service itself to be able to give us this information extremely efficiently. So looking up on the document keys are very effective. Obviously, it's a sub-millisecond level operation. And by the nature of that, we actually make joins very effective. Now, one of the things about optimizing applications is the consistency flag that you mentioned when you come in. In the old world, we actually gave you a very limited set of options. But in the new world, something like this is extremely possible. You can actually have an insert that happened at T1 at the top, so time is flowing. And at T2, you do a whole bunch of other type of operations. At T3, with GSI, what you can express into the system is not only the fact that you want everything to be indexed up to T3, but you can actually say, I just need things to be indexed up to T1. And what that does is it actually allows us to relax the consistency on the index. We don't have to wait 10 milliseconds worth of operations to be indexed before we can actually start executing the query. And that's another important hint to remember when you're coding your applications to really use. So I'll quickly recap, and maybe we've got one or two questions we can take if you have time. But just remember that the architecture and the scalability model that we've set up for these services is very unique. So take advantage of that to tune your queries, number one. Number two, to tune the queries, it is familiar, hopefully, in many ways, back to the relational database world and query tuning. Take advantage of the indexing, understand how to read the execution plan, and understand where the time is spent so you can actually go back and, as system administrators and developers, can tune the environment with the right queries. And make sure to use the consistency dials, because we think that this is going to be a huge gain for the query performance as well, if you actually do it. So with that, I'll close it off and open it up for questions. Thank you. Yes?
Okay, I thought at the beginning you mentioned about it. You're going to talk about a performance benchmark.
Ooh, no, yeah.
Oh, you didn't? All right. Okay.
Yeah.
I was curious because I was waiting for the...
Some numbers?
Something.
So, very good. Sorry I misled you. I did work on TPCC in the past life, but I know I don't have a performance benchmark on this yet. We're still tuning a lot of the performance for this, so the numbers would be fairly invalid.
So are you going to be using the YCSP? Because this doesn't look like it is a good fit for the query performance benchmark.
That is true. So the question is whether YCSP is kind of a good fit, and I agree with you. Yeah, I agree with you. Query performance, unfortunately, there isn't a good benchmark. There's a couple of interesting things we're looking at, but we've got a test suite. I'm happy to discuss that with you as to what we're testing. Yeah, yeah, absolutely. Any other questions? Yes?
On the view consistency dial, if
Excellent question. So if I actually have a mix of consistency requirements, strict consistency or non-so-strict consistency, do they actually impact each other? And the answer is no. We will actually honor whatever you give us. The order of execution doesn't matter. It's just that the one that requires a lot of strict consistency will actually need to wait for the consistency levels to be reached. But that's the only thing. With that, I'm going to close. I thank you very much for coming. Thanks. You want to look up anything else?
Okay, so I think that would be a great topic.
Yeah, you want to.
Too bright. 아.
예.
필요 없을 것 같은데.
So remember that we're doing the live stream, so hold your first slide for a few seconds and make sure to introduce both of yourselves and try not to hide behind this wall too much so that people on the streaming can see, okay?
Yes.